Welcome back. So now let's understand what do we mean exactly by the PCA, which is short for Principal Component Analysis. So let's take a look at this example, right? We have x1 and x2. So how many features we have? We have two features, right? So we have two dimensions. And this is the distribution of the data. This is when we plot the data, this is what we get, right? So if I ask you how many dimensions we have here, we have two, right? The data has two dimensions. But in fact, we can represent the full data using only one dimension, right? We can draw a line here, and after drawing this line, we have only one dimension. Or we can project all the data points on x1, right? So we can project this here, we project this here, we project this here, and so on. And so we need only one dimension to represent the data with 100% accuracy, right? We will not lose any information. So we have two dimensions, but in fact we can represent the full data using one dimension. Now let's look at this example. This can be a little bit trickier than the last example, right? Because we have two dimensions again, and this is a distribution of the data. So for each data point we have a value for x1 that is different from the value of x2, right? So we have here, let's say 5 and 1, 4 and 2, and so on, right? But you can draw a line right here, right? Draw a line like this, and after drawing this line, you can say, okay, this is my new dimension, okay? This is my new axis, right? And you can say this is the new axis, right? So using this idea, we have in fact one dimension, or let's say we can represent the data fully with one dimension, right? Which dimension? This dimension. So it's a combination of x1 and x2. Okay, so although the data has two dimensions, just like this, we can represent the data with 100% information with only one dimension. Okay, so let's take a look at a new example, right? Or another example. Here, this is the same example as this one, but I just moved this data point from here to here and moved this data point from here to here, right? So as you can see, this is the same data distribution, but I just changed some data points, right? So we have some data point here and some data point here. So we have the same two dimensions, right? And you can say that we can represent the data with one dimension or 1.5 dimension, let's say. We cannot say 1.5 dimension, right? So it's either one dimension or two dimensions. So we need two dimensions to represent the data fully without losing any information. But we can use one dimension, just the same line we used before, and there will be some information loss, right? Because when we project this point right here, then it will be here instead of here, right? It's not the same point. So there will be some error coming from projecting this data point onto the line, right? And the same here, right? But here we didn't really have any information loss, because if we draw the line here, then the distance between the new point and the original point is 0. The same here. If we draw a line like this, then the distance will be 0, right? Now, let's summarize this. In the first two examples, we can represent the data fully without losing any information with only one dimension. While in the third example, this example, we can represent the data with one dimension, yes, but some information will be lost. Okay, so we don't really want to lose any information, but sometimes it's better to lose some information if we are decreasing the number of dimensions from, let's say, 100 to 2 or 3 features, right? And we are losing some information, but it's not that big of a deal, right? So let's take a look at another example for PCA. So here we have the data, right? We have these fishes, and we can represent each fish by its height and width, right? So if we plot the width versus the height, we will have this data. And it makes sense, right? Because when the height increases, then the width will also increase. So we have some kind of linear relationship between these two features, right? So we have, in fact, two variables or two features, but you can see that these two variables are dependent on each other, right? So when the width increase, the height increase, and vice versa, right? So this gives you an idea that we can get the shape of the fish using only a single component, a single dimension, a single variable. So let's call this dimension, let's call this variable component, okay? And we call this component the principal component, right? Because it contains most of the information, if not all, right? So how the PCA works? PCA will basically transforms the two original variables, which are the width and the height, into two orthogonal independent components. So what do we mean orthogonal? We mean a dimension like this and another dimension perpendicular to the original dimension. So we call these two dimensions orthogonal. And if they are orthogonal, then they are independent. So there is no relationship, there is no correlation between this feature and this feature, right? So it's increasing like this, while this is increasing like this, can be like this, can be like this, can be anything, right? But if they are in the same direction, right, the angle between the features is just 0, then they are fully dependent on each other. But if the difference in angle between these two features is 90, so they are perpendicular or orthogonal, then they are independent. Okay, so the first component, we call this the principal component because it will explain most of the variation in the data. So this blue line, right, this blue line is the first component because it's the direction with the most information, right? The dimension with the actual distribution of the data. And then we have the second component, right? Because we have two features, right? So we will have two components, okay? And these two components, or this second component, the dotted line, will explain the remaining variations. So if we have two features, we will have how many components? 2 components. If we have 10 features, we will have 10 components. The trick is we are going to use the first k component, right? Because the first component will explain most of the variance. The second component will explain some of the rest of the variance that is not explained yet, or the variations in the data, and the third one will do the same, and the fourth one, and so on. So going to the 10th component, principal component, we will see that it's not really helpful, or it's not adding anything, right? So here we have one component, just like here, one component that can explain the variance in x1 and x2 at the same time, right? So how PCA works? It works by finding the direction, the line, the component, call it whatever you want. So we can say the direction, we can say the line, we can say the component. Which component or which line or which direction? It's the one that has the least information loss. So we will go to the direction with the least information loss. And we can also say it's the direction or the line or the component that has the largest variance, right? So here we have the largest variation. So we can say least information loss or the largest variance. So the goal of the PCA is to reduce the dimensionality of the data. Here we went from 2 dimensions into 1 dimension, right? So the goal of PCA is to reduce the dimensionality of the data while keeping the information loss minimum, because this is just the objective. We don't have this part. Then we can say, let's say that this is a direction that we will choose, right? This is our new component, or the data will be like this. Of course, this is not representing the data because it has a very, very large information loss. So we want to keep the information loss minimum, or we want to minimize the information loss, and at the same time we want to reduce the dimensionality. So this is basically a conceptual understanding for the PCA and a motivation for the PCA. Now in the next lesson we will discuss some of the drawbacks of the PCA, so when PCA shouldn't really be used, okay? And after that we will start seeing the algorithm steps. So we will go step by step into the PCA, the mathematics and the code. So let's go to the next lesson.